Thank you, Eric, again. First of all, I would like to thank everyone. It's good to be here. I just thought about this. This is probably the first AMR presentation I'm giving in the new decade. So I'm going to provide an overview for fuel cell technologies covering 2020 and 2021. And also I'm going to highlight some of the path forward for the years to come. Next slide. We are. Okay, great. So fuel cells convert the chemical energy of hydrogen or other fuels into electricity and are a key element of a broad portfolio for building an affordable, resilient, and clean energy economy. Fuel cells use a wide range of fuels and feedstock and have a wide range of benefits, including efficient energy conversion, reduced or zero emissions, as well as as I mentioned, the use of domestically produced fuels. Fuel cells can be used for power generation in a wide range of applications, stationary or transportation wise, but at the same time, they offer an opportunity to provide long duration energy storage for the grid in terms of reversible systems. Fuel cell technologies applies innovative research, development, and demonstration considering end-use requirements. The end goal in our effort is to be able to develop fuel cells that are competitive with incumbent and emerging technologies across applications. These applications could be as small as putting a fuel cell in a forklift, or as large as putting a fuel cell in a big heavy equipment for mining applications, or for these large multi-megawatt grid applications. What is really important, though, is to know that this process and this effort is application, as I mentioned, application driven. So what we're doing is we have an approach where we're developing and validating concepts to satisfy metrics meeting end use requirements. For that purpose, we come up and we compile a set of targets at the system level per application. And this is really important because, as I have mentioned in the past, all throughout the years that I've been at the DOE, our system level targets are there to achieve competitiveness with incumbent and emerging technologies. They are to drive and assist decommercialization of fuel cells. They're not there just to show where the technology can be, but where the technology should be in order to achieve market competitiveness. On the screen, you'll see examples of system level targets for long haul trucks, for stationary power, as well as for unitized reversible fuel cells for energy storage applications. But we don't stick to the system level targets alone. We are also looking at compiling guideline component and stack level targets, material level targets that would guide the technologies and support the technology development. A key example of that, for instance, is a target that is associated with long haul trucks. And you're going to see this milestone and this target a couple of times throughout my presentation. And that is to achieve 2.5 kilowatts per gram of platinum group metal power for long haul trucks. And this is a target that takes into consideration not only the activity, but it takes into consideration, it's an end of life target that takes into consideration efficiency, durability, and intrinsically cost as well. All our targets are in our multi-year research development demonstration plan. We are in the process of updating that. And throughout the year, we do come up with data records and publications to support our line of thought and what we come out through. So I would encourage everyone to look up our site and especially look at our published data records. Our innovative research development demonstration effort looks at tackling the challenges associated with fuel cells. Those are the main ones that we all know of: cost, durability, but especially for heavy duty applications, efficiency comes into play, as well as the actual power density of the fuel cells. So in the way we try to address these challenges is strategically through an R&D effort, which looks at both the materials and component side, but as well as at the system and side as well, in terms of integrating components, looking at balance of plant, as well as advanced manufacturing approaches with an effort on sustainability. All these efforts are supported by analysis and modeling, and this is going to become evident in the next few slides that I'm going to show you. One thing that I need to note, and that is different than I would say a few years ago, is that we are emphasizing heavy duty applications, and with emphasis on these applications, while for light duty efforts, technology improvement and cost reductions were the main target, we are looking at a harder game here. And for heavy duty efforts, we need to prioritize, apart from cost, obviously, which is always a key factor, efficiency and durability. And it's not only the heavy duty side as well. We can see that by advancing polymer electrolyte membrane fuel cell technologies, we have transferable benefits for medium duty as well as stationary applications. In terms of our funding, we've been stable throughout the last couple of years at the 26 to 25 million mark for 2020 and 21 respectively. As you see on the bar graph, especially for 21, we have an effort that is at the $10 million per year mark for our million-mile fuel cell truck consortium for the core lab of that, as well as a couple of $1 million on ElectroCat looking at PGM-free catalyst development. In terms of what we're looking at, and in terms of what we're going to be looking at going forward, as I mentioned, materials and components, low PGM and MEA component development, other stack component development, including bipolar plates and gas diffusion layers, with a focus on heavy duty applications, as well as longer-term PGM-free catalyst and electrode development, other longer-term technologies, including alkaline membrane fuel cells, for instance. And at the fuel cell system integration side, we have a few projects on stack sterilization for heavy-duty applications. We're looking at BOP components, air management, for instance, our involvement in SuperTruck 3, systems analysis, and advanced manufacturing with a line of sight on sustainability. So I mentioned analysis. Analysis does support our efforts, and it is key, and you will find out why. It's a way to guide our research and development efforts, and it also is a way to gauge where we are in terms of status of technology. And when I say status of technology, a lot on the state-of-the-art lab demonstrated technology and what we need to do in order to make this happen and become a successful reality. So with that in mind, we have been reporting the projected cost of automotive fuel cell systems throughout the years. What has been different in the 2021 framework is that we have shifted our focus on the clear just cost status to include durability as well. Since they both need to be met concurrently, we should have a cost that reflects a system that would be able to meet our 8,000 hours of our ultimate target of durability. And the way we do that is we have a representative power system that's there and projected to meet the 8,000 hours of on-road operation through component design, operating methodology, and stack oversizing. And with that, we have a number which is projected at 100,000 vehicles per year to be at $76 per kilowatt. And not to try to praise our work, but this is a 70% cost reduction from 2008. So all the technology work that we've been supporting, all the efforts out there, and basically this is kudos to stakeholders in the research community at the national labs, industry, and the universities. We've been able to induce these cost reductions through thrifting the loading of the platinum by increasing cell power density, optimizing balance of plant components, and system design as well as looking at innovative manufacturing processes for BOP and stack components. Now, I mentioned we are moving towards heavy duty applications, and might want to ask why. And fuel cells can offer several advantages over incumbent technologies, shifting from diesel to hydrogen, can bring benefits in terms of higher efficiency, zero emissions, higher torque, fast fueling, no noise pollution. And at the same time, we have the potential, and basically we can meet those longer range demands that are important for industry to be viable. We're not only focusing on trucks. A lot of these applications are, in terms of their needs, cross-cutting, in terms of their need to be efficient and durable. So talking about maritime, a lot of our analysis has been looking at expanding our efforts beyond obviously automotive, but even for trucks, expanding in areas where we can look at new system designs to guide our R&D efforts, but also look at the needs and the benefits. For instance, as seen on the screen, there are efficiency benefits for ferry applications. There are lower fuel consumption benefits when you look at rail. And obviously for trucks, and I believe Neha has probably kind of touched upon this in her analysis presentation, there are benefits in terms of emission reductions. And not only that, let's take it one step further and incorporate that societal factor in there, because let's face it, when you have trucks, they operate around their freight depots and usually in areas where air quality improvements would benefit society and the communities around there. So there are benefits just beyond the clear environmental benefits at the broader scale. There are specific societal benefits that can be achieved with this. So we shifted our analysis efforts to look at heavy duty vehicle applications, looking at long haul Class A trucks. The same methodology that we've applied for light duty vehicles, in essence, looking at the FMA approach, looking at taking durability requirements into considerations through, for instance, stack oversizing, not being really stingy on the amount of platinum that we use in these systems. And you can see from the chart there that we have projected $196 per kilowatt at 50,000 units. It moves down a bit lower when you go to 100,000 units at 185. But even at the low volume that one would expect today, we're still over 300, clearly over $300 per kilowatt. So there's work to be done. And our analysis points at what we need to do. First of all, what's different with light duty vehicles is where, the difference between stack and BOP is probably closer approximately to 50-50. We see that the stack cost dominates system cost here. And we're not talking about, in our projected design here, in the system design, we're not talking about a single stack. We're talking about, at this moment, the way we look at it, 4 stacks, which we can reduce down, obviously. But in addition to that, there is considerable amount of platinum in there, because you have to have that platinum in order to meet the 25,000 hours and beyond. So a 60% of that stack is the cost of platinum. And for these systems to gain durability, we are using platinum, not bimetallic alloys. And the stack itself, or the stack cost itself, is close to 70%. That is understandable if you take into account that there's over 300 grams of platinum in these systems. So thrifting down the catalyst would be improving the power density, would be really beneficial in terms of the way we look at our research and development portfolio. There is a pathway, though, to meet our cost targets. Those include, and this is a clear example that I have on the screen here, we can, as I mentioned, we can thrift the platinum group metal with platinum down. We can increase power density. By improving durability, then the oversizing of the stack and all that, the extra beefing up of the system is not required. We need to see and achieve improvements in stack components cost, as well as in the cost of the balance of plant. As for instance, air management, improvement in stack components also would include materials like GDLs or bipolar plates. And then the obvious, increasing production volume. Obviously, we don't have the number of trucks on the road, but as the market expands, as we induce those technology improvements, it just escalates in terms of getting more trucks on the road and being able to move down to reach our cost targets. Now, I mentioned the role of durability. And there are not a lot of trucks out there, for instance. There's not a lot we know in comparison to what we know from our automotive fuel cell demonstrations in the past, or even looking at buses. So fuel cell buses have been out there, they've been really successful. And a key demonstration of that is that we have been tracking the performance and operating hours of buses in various transit agencies. An example here is from 15 fuel cell buses operated from by AC Transit, or those who don't know, the Alameda Contra Costa Transit District up in the Bay Area. We have seen out of those 15, 12 that have surpassed 25,000 hours, including one with over 32,000 hours out there on the road. One thing to keep in mind, though, is that in addition to the operational lifetime of buses, it is important to track the loss of performance resulting from degradation of the fuel cell system alone. We have set a durability target, which is 25,000 hours. That durability target is to 20% voltage degradation, and it was based on stakeholder feedback and end user expectations. You want to have a bus that would be able to go up the hill, for instance. So since we're not really, through this demonstration effort, we're not really tracking system level performance to that level of detail, we've been able to look at relative degradation in fuel economy as a useful approximation for voltage degradation at rated power. So this has been really interesting and really neat, because there's a two-way to look at this. I mean, on the one hand, you're looking at the fuel economy to find out how the system degrades, but at the same time, it really shows that the relative degradation is important, because you don't want to lose that fuel economy, because your benefits get alleviated. So by doing that, and this is status that was based on real world bus data collected between 2011 and 2017. So this is sort of like lower, older technology that's out there. One would expect that newer buses out there would be able to outperform. So that gives us a lot of promise. In terms of that, the bus durability, the way we did this, was determined to be 17,000 hours with less than 20% voltage degradation, or approximating 9,000 hours with less than 10% voltage degradation. So that's a good start to see where we are in terms of these medium duty, heavy duty applications. What we need to do to make the technology successful in this application and in general in all these heavy duty applications is twofold. First of all, you want to achieve a total cost of ownership that is competitive, and that's in terms of getting competitive life cycle costs. And at the same time, you need to be able to meet the durability requirements. You can't envision a truck that would not be able to go up that hill. You're not going to envision a truck that's not going to be able to put the load. You know, load translates into money, into goods. And at the same time, you need the truck to be able to last its lifetime. And we're talking about over 1 million miles and 25,000 of operation. Just to put it in perspective, we were talking about 150,000 miles, 5,000 to 8,000 hours for automotive applications. As you know, by now, we have published our technical system level targets for long haul trucks. The ones that are shown, we have interim 2030 targets, as well as ultimate targets that were based on a competitive life cycle cost. What's really neat, though, is that we are, going beyond this just cost/durability. Once you go and you move into total cost of ownership, the cost of the hydrogen really plays. It is a big deal. Why is it a big deal? Because you have all these hours of operation. You are consuming a lot of hydrogen. The way we can help out on this and add to our goal of reducing the cost of dispensed hydrogen at the end of the day is to be able to have increased fuel cell efficiency. Higher fuel efficiency, lower hydrogen consumption, lower the total cost of the hydrogen throughout the lifetime of the vehicle. So what are we doing to address these challenges? So we have a comprehensive consortium-based effort. Building on our consortia efforts throughout FTO and ERE and DOE in the past, we have established and launched the Million Mile Fuel Cell Trunk Consortium, M2FCT. So what is its mission? To advance efficiency and durability and lower cost of polymer direct hydrogen fuel, polymer electrolyte membrane fuel cells to enable heavy duty application to be a reality in terms of fuel cell commercialization. This is a team's team of teams approach. So we're not looking at a single effort from a single entity. We're looking for a big team comprising of a core team of national labs, but as well as stakeholders, members of the research community from the industry and universities. So our approach has an objective, and that is defined in terms of an MEA target. This is the one I showed earlier in the application, to achieve 2.5 kilowatts per gram of platinum group metal power, or the equivalent 1.07 amps per square centimeter current density at 0.7 volts after 25,000 hours equivalent accelerated durability test. This is a target that takes into account efficiency, durability, since it's an end-of-life target, and intrinsically cost in a single metric. So in terms of the approach, we have, we're not just looking at improving performance and durability as we have in the past. We are incorporating a component and materials development effort. We're looking at integrating these components. We're looking at supporting these efforts by systems analysis, and also looking at manufacturing and components that are just beyond the stack in terms of balance of plant, and integrating those into stacks and eventually into systems. As I mentioned, it's not only the national labs that are involved in this. There are in partnership with universities and industry. The effort includes main laboratories in terms of Los Alamos, Berkeley, Oak Ridge, General, and Argonne, as well as affiliate laboratories, PNNL, Brookhaven, and NIST. But also, as we come up with FOA topics and we select projects, these projects get incorporated into the whole effort. So it's becoming a big happy family, and you can see a lot of the key players on the left-hand side, looking at, as we have incorporated MEA projects, membrane projects, and stack projects, and fingers crossed, as you know, we had a FOA with a couple of topics on bipolar plates and air management in fiscal year 21. I mentioned our effort to look at efficiency and durability of material systems. So in the system that is on board these heavy duty applications, we are mainly looking at platinum because those are more durable systems. We want to look at newer, better materials, looking at platinum intermetallics, bimetallic catalysts that would give you that higher performance, but at the durability requirements to meet the what the application needs. We're also looking at ionomers membranes, and we're incorporating testing and MEAs for performance and durabilities. But it's not only the materials component side. We're looking at getting the fundamental knowledge that's required to be able to mitigate degradation, to enhance durability, to look at more efficient systems. We're trying to look at integrating these components into materials into advanced systems, and using modeling efforts, using experimentation, the excellent expertise that exists in the lab network and beyond, and also look at scaling up and advancing manufacturing approaches. What's really important, though, is as a first step to try to develop accelerated stress test protocols. Why is this important? Because you're not going to take a catalyst and test it for 25,000 hours. You're not going to take a stack even and test it for 25,000 hours. Eventually, that's not going to be the most smart, cost-effective approach. So we want to define an equivalent AST that would be used to gauge durability, and also be used to track our end-of-life target that I mentioned before. For that, we have set up a working group looking at protocols and targets related to heavy-duty applications of fuel cells, looking at accelerated stress tests that could be developed at the component materials level, catalyst, membrane, but also integrated in one complete approach. And for that, we're not being alone. We are extending beyond the US. We are currently establishing international group with representation, not only domestic representation, but from throughout North America, the EU, Japan, and Korea. So what do we need to do for this AST? I mean, the first thing that we need to do is to be able to rely on systems analysis to get the appropriate drive cycles. We need to have those predictive tests. We need to have those accelerating factors. We can rely on what we have for automotive as the experience gained throughout the years, but we have to move that to heavy duty applications. As I mentioned, calculate those accelerating factors and get those tests out there in order to be able to demonstrate and meet our objective for 2025. Expanding beyond the technical, though, the consortium does have core values. Sunita did mention a couple of the activities, highlighted a couple of those activities throughout her in her application in terms of looking at inclusion, diversity, accountability, and equity. The consortium has been working with disadvantaged communities, with historically Black colleges and universities, community colleges, as well as Hispanic institutions. And in that purpose, they've been collaborating with NNSA to enhance a STEM background and education. But as well as that, which is really important, what's really important is the application itself has a potential to favorably impact those disadvantaged neighborhoods and communities out there with improvements to long-haul trucking corridors, for instance, and heavy-duty centers. Let's see, one can see ports, for instance. So let me move to something different now. Longer-term approach. You all know Electrocat trying to advance the development of and expedite the development of PGM-free catalysts for fuel cell applications. What we've done is we relaunched Electrocat, what we call Electrocat 2.0. So this is building on success and world-class capabilities in terms of the lab expertise, the stakeholder expertise, and in terms of synthesis, processing, manufacturing, high throughput characterization and synthesis, and our modeling expertise. The core labs remain the same. What we have here as well is that we're taking a new tool set, looking, for instance, at active learning loop for materials discovery that would include not only advanced modeling and high performance computing, machine learning, artificial intelligence tools, coupled with high throughput experimentation. The other thing that one should know here is that we're expanding our effort not only to look at fuel cells, but also we're looking at that longer term, high impact, low temperature electrolyzer, PGM-free catalyst that could push the needle to lower cost. So relying on the expertise we have in that area to expand our effort. In terms of achievements from Electrocat, there's two things I want to mention. First of all is activity. We've been steadily and strongly advancing the activity of PGM-free catalysts. Over the years, we have an over 2x activity improvement compared to a 2016 guideline baseline of 60 milliamps per square centimeter. And we are expanding our efforts a bit more on the durability side. So it's mentioned on the slide here that ammonium chloride treated single zone catalyst was able to meet that activity. So Electrocat has been looking at ways at advancing that synthesis process. So they've incorporated, apart from the single zone, they have a second, more advanced process which looks at a secondary zone synthesis step. And it's interesting because with the single zone, the one that exhibits the great activity, you don't have excellent durability as one would expect from the systems. But with the second zone, we've been able to demonstrate excellent durability after 80,000 hours. Cycle, sorry, and that's a key achievement. I mean, there's work that should be done to integrate these into MEAs to be able to concurrently meet both our activity and durability, but this is a promising step forward. I have a couple of slides on reversible fuel cells, and we're talking about unitized reversible fuel cells being an important aspect of this portfolio for fuel cell technologies. We have an effort that looks at improving round trip efficiency and durability. What's really important is that we were able to disseminate targets for both low and high temperature unitized reversible fuel cells, and those are going to guide our R&D moving forward. I would encourage everyone who's interested to take a look at those. They're posted on our site. We do have a healthy portfolio of projects, again, low and high temperature, looking both at the material side, but it goes all the way up to a couple of projects that we have with, for instance, Proton Energy Systems and Fuel Cell Energy, looking at demonstrating actual systems. And one example of an accomplishment is and that's just an example accomplishment, looking at the completion of a 50-cell stack, demonstrating excellent round-trip efficiency and durability at the high temperature solid oxide based technology level. So, you know, in the past that I focused on the L'Innovator. What is the L'Innovator? It was established to strengthen and accelerate the commercialization of national laboratory technology in the area of hydrogen and fuel cell technologies. And the uniqueness of L'Innovator was that in our concept, we will not just take certain IP from a certain laboratory, but bundle the IP together, come up with a CRADA, bring an industrial partner in order to de-risk the partner's involvement and move on to demonstrate minimum viable product in an actual commercial setting. What has been achieved this year is that we've been able to fully execute the CRADA between Advent Technologies and Los Alamos, Brookhaven, and NREL. Los Alamos bring their high temperature membrane technology in terms of their ion pair MEA. Brookhaven bring their core shell catalyst technology, and NREL their manufacturing capability. And at the same time, Advent brings their commercial aspect as an industrial partner that specializes in high temperature MEAs. It's to leverage both Advent's commercialization experience as well as its relationships with volume manufacturing to scale up to manufacture and be able to demonstrate that minimal viable product. So I'm going to wrap up nicely by, first of all, mentioning the extensive collaboration network that we have in the office, in DOE, across the government, domestically and internationally. So these include cross-agency collaborations. They include industry engagement through US Drive, as well as 21st Century Truck. The consortia themselves have international collaborations, especially focusing on test protocols and best practices, and all at the pre-competitive level, as well as IEA collaboration opportunities. I also have a slide on our highlights and milestones. These range from 2019 to 2020. I mentioned some of these throughout my presentation. We do have milestones for 21. Some of these, like our improved platinum group metal free catalyst activity, have been achieved. We've been able to establish a durability adjusted cost for trucks to get the ball rolling in that area. So we have a few other highlights that, milestones that we want to complete by the end of the year, and also a list of milestones as we move on and are listed on the slide there for 2022. So progress to be seen and to be achieved. And for that, we need help. As Ned mentioned in his application, we are also looking at hiring candidates for fellowships for fuel cell technologies. And for application, for those who are interested, I encourage all of you. It's a great environment to work in. It's a really exciting time as well. There is the site that's the link that's shown on the slide below, or you can contact Greg and Donna for more information. And if anyone asks who's Greg and Donna, I mean, first of all, you should know who they are. But even if you don't, let me tell you, they are a part of an excellent team. It's a talented and exciting team. I would like to thank all my coworkers for the hard work they put through in the last couple of years. Dave, Donna, Greg, Will, John, and Eric have been exceptional. And with that, I would like to thank you for your attention. I'm going to hand it over back to you, Eric.
Well, thank you very much, Demetrius. And that brings us to our first break of the afternoon. So we'll be resuming the session at 2:45 with an overview of our technology acceleration program. So thank you, and join us back then at 2:45 Eastern Time.